Without further ado, I'll introduce our first speaker. Some of you met him last night at the panel discussion, Dr. John Hayes. Dr. Hayes is a freshwater fisheries scientist from Nelson, New Zealand, recently retired from the Cawthron Institute, where he retains an emeritus position. John has special expertise in recreational trout and salmon fisheries, in-stream habitat modeling, and salmonid foraging and bioenergetics modeling. He has led and supervised research and consulting projects on freshwater fisheries habitat assessments, limiting factors, environmental flow regimes, and effects of hydropower and irrigation schemes. Over the last 2 decades of his career, John led a series of research projects with New Zealand and United States scientists developing process-based models, integrating river hydraulics, invertebrate drift, transport, energetics of drift feeding to predict effects of flow, water temperature, and clarity on streams, salmonid growth, and carrying capacity. Much of his research has been aimed at understanding how rivers work in relation to sustaining fish populations and fisheries to inform environmental effects assessments. He has undertaken fisheries-related environmental consulting widely in New Zealand and contributed to a project in Oregon. His salmonid bioenergetics modeling have been applied in New Zealand, Australia, and the United States, including the North Umpqua and Colorado rivers and Columbia River tributaries. John's interest in fish ecology arose from a lifelong passion for fishing. Over his career, he has enjoyed communicating freshwater ecology and fisheries science in popular press. He has been a regular writer for Fish and Game New Zealand magazine, also published in Fly Life magazine Australia, and co-authored the book, The Artful Science of Trout Fishing. John's had an impact on my career vicariously through his students. A while back, I attended a conference where saw several talks on drift foraging and bioenergetics modeling, and it's really impacted the direction of my research in the last few years. And everybody, welcome Dr. Hayes.
Thank you for that introduction. It's quite an honour for me to be invited to talk to you today, to stand in this state, not far from the place where the United States gave a precious gift to New Zealand. And that gift so influenced my connection to and discovery of the natural world of rivers and lakes. In the late 1880s and the first decade of the 1900s, the USA gifted several batches of Chinook salmon and rainbow trout over to New Zealand from the Beard Hatchery on the McLeod River, just over the hill from here in the Central Valley. And in the latter stages of those introductions, this man, Lake Ayerson, who was the first Marine Inspector of Fisheries in New Zealand, he ordered those shipments of ova. And it was his vision that established Chinook salmon in New Zealand. And unlike others before him who had tried and failed to introduce Chinook salmon to New Zealand, he had the vision of making big introductions on one river, the river most likely to provide the best habitat and the most chance of establishing Chinook salmon. And that was the White Snowmelt River on the east coast of the South Island of New Zealand, and it drains New Zealand's highest mountain, Aorangi or Mount Cook. And from those, and he was successful in establishing Chinook salmon there. And from that river, Chinook spread to all of the rivers that could support them on the east coast of the South Island. And also there were some introductions on the west coast of the South Island, and they established minor fisheries there as well. Yeah, and so the New Zealand government's mission in those days was to establish commercial salmon fisheries like occurred on the western seaboard of North America, but unfortunately runs of that size didn't eventuate. But we did end up with some reasonable recreational fisheries for salmon, and Lake Ayerson's legacy also extended to, in the 1990s, the establishment in New Zealand of a significant salmon aquaculture industry based on cage rearing. Now, where I started from, in my interest in lakes and rivers and fishing, that came from my father sharing his passion of fishing with me. And so I grew up in Christchurch on the east coast of the South Island, halfway down the island, and right in the middle of Chinook salmon fisheries, very close to some of the best rivers in New Zealand for fishing, and also surrounded by abundant opportunities for trout fishing. So the efforts of the acclimatisation societies in New Zealand from way back in the 80s, not 1880s and into the 1900s, to introduce trout and salmon into New Zealand was spectacularly successful. And you can see here what resulted from that in the distributions of brown and rainbow trout and Chinook salmon around the country. And as might be expected, with a great spread of invasive trout in particular, and brown trout in particular, there have been some significant adverse effects on aquatic ecosystems and native fish in particular. But that's another story that I haven't got time to talk about today. So paradoxically, those introduced fisheries for salmonids, they became New Zealand's most important, economically important and socially important fisheries. A lot of our native fishers don't support fisheries. Some of the glaxids do, but we had no fish in New Zealand that had the charisma and size of salmonids. Eels were the main fish that Māori relied on. They call them tuna. But no one comes from the other side of the world to go and catch black slimy eels like they do for salmonids. And they've significantly contributed to New Zealand's outdoor culture and heritage. And so why did I end up specialising in my research career, which started on an interest in fishing for these fish? Why did I end up focusing on salmonids other than native fish? And the reason is because these fish matter to people in a serious way. Salmon have also shaped not only the freshwater values in New Zealand, but also water wars around environmental policy and also environmental policy and research in New Zealand. Trout and salmon, as you well know, because of their size and behaviours, have very high water flow requirements and water quality requirements. So they've been at the centre of water wars in New Zealand, and I've been in the midst of that. I've lost count of the number of hearings, resource consent and environment court hearings I've been involved with, and they're very contentious. And the fishing licence revenue from angling for these fish have bankrolled the environmental advocacy for freshwaters in New Zealand. And salmonids have become the inconvenient fish to hydropower managers and the agricultural industry. If it were not for salmonids, those industries could get away with taking a lot more water out of rivers because most of our native fish are relatively small and don't have the high flow requirements that salmonids do, except for one or two. So my research career was very much influenced by the need to provide environmental flow assessment advice to these hearings. I got involved in a lot of resource consent hearings, as I say, and environment court hearings, national water conservation orders on rivers, and also contributed to the regional water authority water plans around the country. And so that's very much influenced the colour of my research. So to get onto the main subject today I'm talking about, how does flow reduction affect drift feeding salmonids? And you know a lot of this already. So as you know, flow alteration can affect the water temperature and oxygen regimes of rivers, but in run-of-the-river cases, like for example, just a run-of-the-river irrigation scheme, you have to take the river down very low, the flow very low, before you start affecting water temperature and dissolved oxygen. And by that stage, the carrying capacity and habitat and carrying capacity has already been impaired. But with water storage reservoirs, like you're dealing with in the Trinity, as you well know too, you can alter the temperature regime quite radically. and have to account for that. And flow alteration can affect fish movements, as you well know, either the timing of runs, smolt migrations, adult migrations, and very low flows can present passage barriers for fish. Flow alteration also affects in-stream habitat for fish, and that can be positive and negative depending on the size of the fish. Very large rivers, you can get away with taking some flow out of the rivers and maybe benefit small fish. But when the river gets very low, both small and large fish are affected. And it also, flow alteration affects the benthic invertebrate community and the drift food supply. And those two things can be more sensitive to flow alteration than fish habitat itself. And as you'll see later in my talk, the drift transport capacity of the river and how flow affects that can be very important. When we provide advice on environmental flow requirements of rivers, we start with hydrographs and look at the key features of hydrographs that have some physical or ecological function, and provide advice on how much you would need to reserve those. And the first is channel forming floods, and for there you need a geomorphologist like John Buffington to come along and give you advice about what size and frequency of large channel forming floods are required to keep the channel form. And then there are flushing flood requirements too, smaller floods, and they control the periphyton biomass. You don't want periphyton proliferations in the river. So again, the magnitude and timing of those is important. And then there's the minimum flow that you might set on a river. And often when that's done, people who want water out of rivers then say, well, the job's done. We've set a minimum flow, we can walk away and take the water above that. The water that's shaded in blue here, or the flows that are shaded in blue, that's the part of the hydrograph often that everybody fights over. And my job and much of my career has been targeted at trying to figure out and explain to people who want to use water what function that part of the hydrograph serves. And there's two key functions for ecosystems and fish. And one of them is that those flows support benthic invertebrate production over and above the production that's provided by the minimum flow. And those flows are also transporting invertebrate drift for providing fish feeding opportunities for drift feeding fish. And you'll see the significance of that later. Now, traditionally, a lot of environmental flow assessment, especially using hydraulic habitat modelling, which we'll cover in a minute, has focused on the habitat needs of the trout, so the depths and current speeds, the substrate composition and cover needs of salmonids. And you can see here that small fish like to live in shallow places like riffles and shallow runs. And as salmonids grow, they need faster and deeper water for their feeding and behaviours. And so they move into deeper water. And also the shallow parts of the river is where the invertebrate production's going on. Now, just to emphasise to you the importance of food production, I'm showing here the results of hydraulic habitat modelling. In New Zealand, we have habitat suitability criteria or curves or models, habitat suitability models. Let's call them habitat suitability criteria to encompass all of those types of models. We have those for trout and salmon, often imported from North America or somewhere, some of them developed in New Zealand. We've got them for most of our native fishes, and we also have them for most of our benthic invertebrates or just general food producing benthic invertebrate habitat. And I'm showing here the results from hydraulic habitat modelling for one of those sets of benthic invertebrate habitat criteria, actually imported from Colorado, are describing the depths and current speeds that you find invertebrates in moderate-sized trout rivers. And comparing that with the weighted usable area, or the habitat score for a reach for adult trout, about 50 to 60 centimetres long. And those suitability curve sets or models were developed in New Zealand by me and Ian Jowett. And you can see here that the flow requirements of the benthic invertebrates are higher than the large trout themselves. Now, that food-producing habitat, the shallow parts of the river, is highly sensitive to flow reduction, especially when you're dealing with small rivers at the low flow part of the hydrograph. And so the wetted width of the river shrinks, and the amount of inundated habitat that's available for benthic invertebrates decreases quite quickly. And the other thing that's happening when that's going on is that the drift transport capacity of the river is winding down as well. So less food on the bottom for invertebrates. The paddock size of the river is reducing. I try to get that across to farmers when we're debating about the flow needs of fish and river ecosystems. As the paddock size is reducing and the transport capacity of the river is winding down. Now, whether the habitat reductions for fish and for invertebrates and the transport capacity of the river for drift is winding down, whether that's important really depends on whether fish are food and habitat limited, and that's a very difficult thing to determine. Now, to emphasise the importance of food, including food in environmental flow assessments for fish, I've got a few slides here just to show that. And the first comes from a study in New Zealand by Ian Jowett, a guy I used to work with a lot and learnt my trade in habitat assessment, habitat modelling from. He did a big study in the 1980s and early 90s on a lot of rivers in New Zealand, clear water rivers, about, in this case here, about 40 to 50 rivers, estimated the trout abundance by drift diving, and then had a whole bunch of environmental variables where he tried to correlate those with trout abundance. And two of those were flow-related habitat variables, and one of them was the amount of trout habitat available the quality of the trout habitat available at the mean annual low flow, and the quality of benthic invertebrate habitat at the median flow. And he also used benthic invertebrate biomass to correlate against trout abundance. And he found that both the trout habitat at the mean annual flow and the quality of benthic invertebrate habitat at the median flow were related to trout abundance. The highest correlation he found was with benthic invertebrate biomass alone, which explained 45% of the variation in trout abundance. And a model that included the weighted usable area, or the quality of habitat for trout at the mean annual low flow, and benthic invertebrate biomass explained 64% of the variation in trout abundance. And here's a graph from another one from New Zealand showing the relationship between invertebrate biomass and fish community biomass, quite strongly related. And then a figure from Columbia River tributaries in Oregon by Nick Weber, who worked with Nicholas Nick Bowes on the upper Columbia tributaries, a big research program involving bioenergetics as well. And so Nick Weber here found a good relationship between benthic and invertebrate biomass and drift biomass. So those two are related. And another study by that crew on the Columbia River tributaries showed that as the drift biomass increases, the ration size for the fish themselves increase. So the p-value here is the proportion of maximum rations that's predicted by a bioenergetics consumption model. It's affected by temperature. So you account for temperature where the fish is feeding, and then see, and then you can work out the consumption that they would be able to have, or the amount of food that they would be able to consume. and compare that to what you see in the real world. By actually looking at how much consumption the fish are experiencing. So the point is that the more food there is, the more drifting food there is available, the more the fish eat it essentially. So I started my environmental flows research in the late 1980s, and I had a good grounding in hydraulic habitat modelling from Ian Jowett, who was New Zealand's expert on that. And just for anybody in the room who doesn't know about hydraulic habitat modelling, it's essentially a model either based on cross-sections in a river or bed elevation data that can figure out the depths and current speeds throughout a surveyed reach and how those depths and current speeds change as the flow changes. And that can be used then as a template on which to assess in-stream habitat. So there are habitat suitability curves that I talked about before, the current speeds and depths that fish like to sit in or live in. And you compare that to the current speeds and depths that are predicted by the hydraulic model. And each point in that reach that's been modelled represents an area. And so you can weight up the habitat score for each point that you get from your habitat suitability curves or models by the area that point represents, and sum that for the reach or average it for the reach, and come up with a habitat score for the whole reach, which is shown here on the top right. In this case, it's called WA, or weighted usable area, or it can be sometimes called area weighted suitability. And so that's the currency, those curves are the currency that's used for flow negotiations in rivers. Now, when hydraulic habitat modelling came out in the late 1970s and through the 80s, it was mired in controversy. A lot of research, a lot of fish biologists and anglers thought that the results were too simplistic and criticised it roundly. And so in a lot of hearings that you get involved in around flow needs of fish, you got mired in debates about the accuracy or reliability of the predictions of that model. And if you're unaware of that, then have a look at this paper up here by Steve Railsback, who covered that. So here are some of the limitations of simple hydraulic habitat modelling. First of all, it's very difficult to develop unbiased habitat suitability criteria. The habitat suitability criteria that you go and you look at a river and find out where the fish are, measure the current speeds and depths, and do that for a whole bunch of fish. Or you could do it for invertebrates and come up with a relationship where, what are the preferred current speeds and depths the fish like to sit in. Those habitat suitability criteria tell you where the fish are, but not why they are there. And so the bioenergetics models that I'll talk about later tell you why they are there. This method also overlooks other key flow-related variables. First of all, as I've been talking about, traditional habitat modelling based on habitat for fish alone overlooks the effect of flow on benthic invertebrate habitat. And also, the method overlooks the influence of flow on the spatial distribution of invertebrate drift for drift feeding fish, and the drift foraging behaviour of the fish, how that's affected by flow itself, and how the two combined to influence habitat selection. And of course, it overlooks the role of invertebrate drift transport in affecting where fish are, but particularly the instantaneous carrying capacity of fish. But I don't advocate throwing out hydraulic habitat modelling entirely. It's still really useful. The first thing you should be doing, but building on that, better models that use that hydraulic modelling platform, models that include more biological realism. And that's what these bioenergetics models do that I'll be talking about now. So because of all that controversy, I had a vision back in the 1990s to come up with some method of loading into these hydraulic model platforms, models that had better biological realism, and they were these bionogenics models. And to get there, I was very fortunate that I was able to partner with some very bright people, some of them much brighter than me. And without them, without that collaboration, we would never have achieved what we came up with. I first of all formed a collaboration with Nick Hughes from the University of Alaska, Fairbanks, and his buddy Lon Kelly from BLM in Fairbanks. And they coded some of the first versions of the models that we were working on. And then after that, around 2010, again, a serendipitous moment in my life, Eric Goodwin fell into my lap, and he was a data analyst and modeler at the Cawthron Institute, employed for other reasons. And I found out his capability and snaffled him and brought him into my program. And without his coding ability, I could never have achieved what we ended up. So my role was sort of conceptual vision. I can do some coding, but nothing like these guys. So I just teamed up with some really bright people. And also Karen Shearer, who provided the invertebrate drift and benthic invertebrate expertise throughout the programs. Joe Hay, who provided field help and also documentation of some of the modelling. And I teamed up with Murray Hicks from NIWA, National Institute for Water and Atmospheric Research in Christchurch. And he's a sediment transport modeller, and so he came in really handy when we started to model invertebrate drift transport. So these models that use bioenergetics foraging modelling or modules in them, they are based on, they predict net rate of energy intake for drift feeding fish, and that's the difference between the energy intake that the fish gets from the drift minus the energy costs in swimming and feeding and metabolism. And the foraging models are based on visual foraging equations that have been worked out on little fish in the lab mostly. How far away that the fish can see a prey, just like you or I, you can see bigger things further away, so bigger invertebrates are seen further away. And then there's a sort of a concept where the fish sees a prey coming along, drifting along, turns to go to intercept it, and there could be some rules about the fish has to intercept the prey before it's swept downstream past the fish's position. And if you know the current speeds, the swimming speeds of the fish, the speed of the prey, you can work out through Pythagoras' theorem the maximum capture distance, how far away the fish would need to go to capture that invertebrate. You know the swimming speeds of the fish while it's doing that, so you can work out the swimming costs, and so you can work out the prey interception fields. That's what's shown here in cross section from the visual foraging equations. You do that for different prey sizes, and that's what these dotted boundaries are on that blue diagram there. And the dots are the actual prey interception locations figured out from underwater stereo imagery from video cameras with some very fancy software that can reconstruct in three-dimensional space all the foraging manoeuvres of the fish when we're testing these models. And that technology came from Nick Hughes and Lon Kelly. So the other part of the equations, or the models, are the cost equations. So that's the costs of metabolism, digestion, and excretion and activity. And they're all temperature dependent. So these models account for the temperature effects on the fish, the food effects on the fish, and then the habitat over which they're foraging, and the food supply. So the foraging model that we started with was a simple one, developed by Nick Hughes, and that built on the knowledge of drift feeding by himself and others, and including Kurt Fausch in the audience here. And that's that simple one I just talked about before, where the fish intercepts the invertebrates to its side, and you can calculate the maximum capture distance. The models calculate the capture distance over a series of radials out from the fish's position. You can see there on the top right figure, and the water velocities are varying along those radials, and from that you take that into account to work out the capture distance. Because the faster the water the fish is in, it can't go out in real fast water, it can't go out as far as it can in slow water before the invertebrates swept past its position. So you end up with this irregular capture area. So unfortunately, we lost Nick to depression in 2009. That was a real tragedy. He was a great friend of mine. He came out to New Zealand frequently, and yeah, it was devastating. But those that knew him with his untidy hairdo at conferences would relate to this point he made about mechanistic foraging models and process-based models. They serve to summarise our progress towards understanding drift feeders and as practical tools with which to predict their behaviours. The first time I used one of these foraging models, it was based on Nick and Larry Dill's model, and I thought, gee, can we use this to predict the growth rate of trout? So I set about doing that in the Marua River in the South Island of New Zealand, above falls population of trout. And we had the temperature regime, annual temperature regime. We had drift data taken seasonally. We had fish that were caught by angling, including by me. So we had size at age data from otoliths, and so we were able to plot a growth curve, observed growth curve, and make predictions with the foraging model. It's a whole lifetime growth model that accounts for reproductive costs as well. And that assumes that the fish loses 50% of its energy once it starts reproducing every year. That makes the growth curve tip over and flatten out like you can see there. And it was really quite successful. We had a really good prediction of growth rate relative to observed growth rate. So that gave me confidence to carry on with those models and come up with a carrying capacity model that could be launched off a hydraulic model to predict the effects of flow change on fish abundance. Before we did that, we did a lot of work on testing of the models. And here's Nick looking at his video screens, underwater stereo imagery, and Lon Kelly with a big drift sampling array on a river in Fiordland in New Zealand. So that's the behaviour that we were observing, and we were seeing whether the foraging model predictions matched what the fish were doing in the real world. So you guys are interested in, little salmon smolts, or salmon power and to salmon smolt stage. I was interested in going beyond that to big fish because our trout stay in New Zealand rivers to quite large size. 50 centimetres is sort of an average that anglers would catch. So that's why they have big flow demands. So a lot of my work was around that, but you can scale these predictions down to small fish as well. So this just gives you an idea of some of the predictions of the foraging models when we were testing them with the data put into plan view. Again, the predictions of the foraging models there, you can see the foraging window and the different prey detection prey interception boundaries depending on prey size, and where the prey interceptions took place relative to the model predictions. And you can see there on the top right that the 3 dimensions of the foraging window, of the foraging area. And here's a view of, in cross-sectional view of some of those tests. And also on here are prey capture probability contours as well, which we figured out. So it's just to give some illustrations on some of the testing we were doing. We found that the models made reasonable predictions of the size and shape of the foraging area, and also that prey capture probability declined with distance from the focal point. Now, some of these things have been found out by other people as well, and more testing has been done by others. And those refinements have been included into the foraging models that we now use in these big process-based models. And this slide shows you how the process-based modelling approach, how it works and the components of it. You start with a hydraulic model. In this case here, it's a two-dimensional hydraulic model predicting depths and current speeds throughout the reach with a heat map there of current speeds and depths. And from that hydraulic modelling platform, we run a drift transport model. That model is based on sediment transport theory. So just to segue a bit here, the drift we're talking about is passive drift. It's not the active drift. It's not the invertebrates, the terrestrial invertebrates and the aquatic adult invertebrates drifting on the surface of the river. It's not the active drift that when invertebrates want to hop up into the water column to drift to somewhere else they'd prefer to be, or because they're emerging. It's not that. It's passive drift driven by flow. It's the drift that accidentally dislodges invertebrates from the bottom. So in that regard, you can think of the invertebrates as a particle. So therefore, their drift behaviour should be related to what we know in sediment transport theory. So just a particle with various traits, characteristics that determine their stickiness on the bottom. So as the flow goes up, the velocities increase, the shear stresses increase on the bottom, and they start displacing particles, including invertebrates, off the bed. So that's what this drift transport model does. It works, it takes into account the entrainment rate of the invertebrates, the settling rate, the dispersion of the invertebrates, and you feed in drift at the top end. You calibrate the drift model to observe drift concentrations down a reach, that you do some sampling, and then run the model at different flows. And then, so now you've got a habitat and food template, drifting food template that you can interrogate with the drift foraging model. So in these models that you see there, the coloured ones, you put a whole bunch of virtual cross sections in the computer, very closely spaced together. And for these size fish, we had them 1/2 metre spacing. And so you interrogate along those cross sections and find out, oh, where could you have put a fish? Where's the what net rate of energy intake are you getting across those cross sections? And the first thing you do is say, look through the whole reach, find the best spot for NREI and plonk a fish there. And you can have a criteria to turn a continuous variable like NREI to a discrete one. And that is, you could say that the NREI has to exceed 0 in order to have a fish there. So that would mean that there's enough energy for the fish to maintain its condition. And if the NREI is higher than 0, it's got enough energy to grow. Or you could have a criteria that a fish has to get enough energy to be able to reproduce annually, and you could plonk a fish there in that position. So choose the best spot in the reach, plonk a fish there, then that'll put a hole in the drift, it depletes the drift, and the drift dispersion model then redistributes drift, and there's more entry going on. At some point downstream of there, you can plonk another fish in the computer. And then across the cross sections, you can plonk fish in as well. So this map, so there's the difference. That last one I just showed shows the fish, the NREI heat map, and then the fish being put in and then depleting the drift. So this model is predicting instantaneous carrying capacity, and that's always changing as a function of flow, temperature, and drift concentration and rate. And so drift concentration is also a function of the benthic invertebrate density, and that's always changing as a function of variable flood and drying disturbance and subsequent population accrual rate. Now, this is a pretty nifty thing to see. This is an R, and this is where we got to in sort of the research and the research part of our modelling, a test of the model to see whether it made sense. What you're going to see here, there's a drift sampling array, there's a pool in a river in New Zealand where we tested the model. You're going to see now some predictions of the model showing NREI contours or heat map and the predictions of fish locations as the flow increases at a constant temperature and a constant delivery of food into the top end, drift food in the top end. And you'll see that the numbers of fish change as this animation goes forward, and their positions change as the flow goes up. So one of the neat things about that was that it showed that as the flow went quite high, the only places where fish could actually sit or make a living were in little indentations along one boundary, one bank. So that's what you'd expect to happen. I think the other thing was that the model accurately predicted the numbers of fish in the pool. There was about 6 to 7. So from that, we said about scaling up to large rivers. And for big environmental flow assessments, there were 4 rivers that we tried this model on. We got a better drift transport model and went to it. And so there's the Matilda River, the Cawthron River, which is the one bottom, that one down here, the bottom left, that's 200 cumex. The other ones are around 4 to 30 cumex. And one of the things I found early on in doing, when we were scaling up to large rivers, was we wanted to see the relationship between invertebrate drift and flow. And we found that the drift concentration declined as the flow went down, and that was very, very significant to know that. And if I was a sediment transport modeler, I'd have known it anyway, because on first principles, you'd know that as the flow goes down, the river transports less sediment and sand, for example. But sometimes biologists need to reinvent the wheel. So that's drift concentration, and drift rate also goes down. So drift rate is the, in this case here, of flux. It's the amount of numbers of invertebrates passing a cross-section in a river. And that's the product of drift concentration and flow. So flow there is directly related to drift rate. So that means that a halving of flow will halve drift rate. In fact, the reduction is more than that because drift concentration goes down as well. So drift transport is highly sensitive to flow reduction, more so than the habitat for invertebrates and for fish. So I was interested to see how these new models, their predictions compared with traditional habitat modelling, and whether the habitat suitability curves that we were using in traditional habitat modelling made sense. Here's 2 predictions here of traditional habitat modelling, weighted usable area against flow for 2 habitat suitability curve sets or models, one from the South Platte River by Ken Bovey, and another one that I developed on New Zealand rivers with Ian Jowett. And they differ, and so which one do you believe? And here's the predictions of the bioenergetics process-based modelling for the Matilda River. The first thing to look at is on the top right, and that flat curve there, which is the predictions of the model, predicted fish numbers as a function of flow. If you assume that drift is constant, drift concentration is constant across the flow range. And you can see that sort of matches a bit with the Bovey habitat suitability curve predictions. But when you account for flow varying drift concentration, so drift concentration goes down as the flow goes down, and feed that in at the top end of your model, you get a radically different prediction. So it shows that you need quite a bit higher flows for fish, for trout, than what you would predict by habitat modelling. And here's another prediction from the Aparima River, again comparing some predictions from hydraulic habitat modelling. On the left-hand side here, the hydraulic habitat modelling predictions for a range of habitat suitability curves, some from North America, some from New Zealand. And then the predictions from the process-based bioenergetics modelling on the right-hand side. for flow varying drift concentration. And you can see some matches between the drift so the predictions from the foraging model approach for large trout, which is the bottom one, the bottom graph, the brown one. They seem to match reasonably well with the habitat suitability approach with habitat modelling. It also shows here the scaling of the predictions from the process-based model for fish size. So the smaller the fish are, that's the top graph over here, top right, smaller fish have lower flow requirements. And again, that makes sense. So does the drift NREI modelling, process-based modelling approach make sensible predictions for fish abundance? Again, from the Aparima River, Fish and Game did a drift dive of the reach that we were modelling there, and they came up with 39 trout in the reach, 32 per kilometre after a prolonged low flow period. And the NREI modelling approach predicted between 0 and 89 trout, large trout, over a flow range of 0.2 to 8.7 cumex, 20 large trout at the mean annual low flow, and 29 trout at the Q95 flow. But anyway, the NREI predictions fell in the same ballpark as the drift dive count. So that's reassuring, bearing in mind that carrying capacity, instantaneous carrying capacity, is varying all the time. And here's just, you can play what-if games with these models. You can learn a lot about, like Kurt did a lot of work in the field trying to figure out how drift affects fish. But you can play those games in one of these models in advance and see what happens. If you change, in this case here on the Ariti River, if you change the drift concentration by 4 times, starting with the observed drift concentration multiplied by 4, you radically increase the fish numbers, and you can see where the model was predicting they should be. And another thing you can play is, in this case here on the Ariti, what happens if you have constant food, in this case here on the top right, on the top left, 2 different drift concentrations, 4 times difference. What happens if the food is constant over a temperature range? And you can see as the temperature goes up and the consumption requirements of the fish go up, which is shown on that graph over there, goes up exponentially. If the food doesn't keep pace with the temperature, then the carrying capacity for the reach drops dramatically. But fortunately, in the real world, as temperature goes up, the production on the bed increases as well because it's temperature related. And so there should be more food there. So there's some practical advice comes from all this complicated modelling, and that is that fish habitat modelling alone, from hydraulic habitat modelling, that alone can underestimate the effects of flow alteration on drift feeding fish. Drift transport capacity can decline with flow reduction, and it's highly sensitive when it does to flow reduction. And reduction in drift concentration in energetically profitable feeding locations with flow reduction, they combine to drive down the instantaneous carrying capacity for drift feeding salmonids. And the effect is non-linear, and it's relative to fish size and river size. And drift transport versus flow relationships complement traditional hydraulic habitat modelling. And drift versus flow relationships alone can tell you something. They can inform the effects of flow alteration in that blue band I showed you on the hydrograph. You can just use that alone to show the effect of an allocation on the percentage reduction in drift concentration. So a percentage reduction in flow translates to a percentage reduction in drift concentration or rate. So I'll leave it at that. If I have any more time, do I? Probably not. Okay, just I was talking to some people yesterday that they had an interest in another bioenergetics model, and it's called Bioenergetics HSC. And I was involved in that paper and model development. But it was done primarily by Jordan Rosenfield and Sean Naiman and Jason Newswanger. And Jason was the brains behind the coding. So this was an attempt to bring into traditional hydraulic habitat modelling some bioenergetics capability. So the model makes bioenergetics-based habitat suitability curves based on drift foraging models. So I just want to raise the concept with you. It was published in Fisheries magazine, and the idea was to try and make these sorts of energetics modelling, so that capability available to people and to be able to use in conventional hydraulic habitat modelling. So the models can make habitat suitability, bioenergetics-based habitat suitability criteria, surfaces in this case here, for any size salmonid, and you can the input to that is water temperature and a drift data set. So, and you can make the drift data sets up. You don't necessarily have to have them from the river. You can look at other rivers and look at size structures of invertebrates, of communities, drifting invertebrate communities, and feed that into the model. You can also, with those models, figure out, gee, is there a relationship between drift concentration and flow? And if there is, then make habitat suitability curves like this, or models for each concentration, and then feed that in to a modelling exercise where you have, for different flows, where you're modelling habitat, you have a different drift concentration and therefore a different habitat suitability model set. So those models give you a step up in bringing in bioenergetics into habitat modelling. They don't include a drift transport model. They don't account for drift depletion by fish in a reach, but they get you somewhere into the bioenergetics realm in habitat modelling. So if anybody wants to talk about that later, I can cover it in discussion.
Yeah, hi. What you're talking about right now is exactly what I'm interested in asking you about.
We were talking before.
Yeah, right.
Yeah.
Because the software we're using we're dealing with spatially constant drift, and that's something that kind of worried me while we were working on it, and I'm wondering how big of a deficiency is that in your mind, that we're just putting in these drift files and it's not doing any of that entrainment stuff or any of that. And do you see a way we could, well, you just said it, we could have a time series of drift input to deal with the concentration. But I'm just kind of curious about, what you might say about how we can try to be a little more realistic with what we're doing, or if we can get a hold of a different model, maybe.
Yeah, well, what you just said, making habitat suitability models for different drift concentrations over a flow range is the way to step up even that model that I just showed you. The research hasn't been done, and I didn't have time to do this as I was sort of running to keep up with this modelling and applying it. The research hasn't been done to step back and say, okay, how do the predictions from the various models and assumptions, how do they compare? And so how does the bioenergetics HSC predictions, I'll just show you, that model we're talking about now, how do those predictions compare with the full noise model that I was running on some of my applications? And does it matter if you don't allow for drift depletion by the fish in a drift transport model? We don't really know. So all I'd say is that what you're doing with this bioenergetics HSC model is a really good first step, and it'll give you a step up in hydraulic habitat modelling. Well worth doing, especially if you include the drift varying flow. Now, I don't know whether you know, but I wrote a report on that model that describes how to use it, because I knew when the fisheries paper came out in Fisheries magazine that it would hook people in, but it might not provide enough information for people to run it. So there's a Cawthron report I wrote that I can link you with if you haven't already seen it.
Yeah, I haven't seen that, but it sounds like we can talk Which is lots to talk about here. So,
Yeah, right. Okay.
thank you.
Hi, John. Thanks for that presentation. It was very, very enlightening. I learned a lot from it. You mentioned NREI being dependent on food supply.
Mhm.
And, for our juvenile salmonids, not all benthos are food, and that changes as they grow. I'm wondering if you could speak to some of the challenges and opportunities in incorporating benthos community structure and how that changes seasonally into the NREI model. So, getting a handle on what the food supply is and how we can better, use that information for NREI.
Well, you do that by seasonal drift sampling and benthic sampling. And I understand that there's interest in doing that in the Trinity. So you've got that's your foundation. I wouldn't get too tied up with subtle differences in community structure and the energy differences might be there. The most important thing is the drift size structure and the total density. Concentrate on that, because there's all sorts of errors in these models that whether they compound or not, who knows, but the research hasn't been done enough on that. But you don't want to get too detailed because the errors in the models will swamp that. Yeah.
Thank you.